Good morning, guys. Today we're going to go through the notes, the first part of the notes for section 9, the last section on graphing trigonometric functions. In this section, we're going to go over inverse trigonometric functions. Your objectives are found on page 853. You could go ahead and pause the video and copy these down. I'm going to assume that's what you're doing, and I'm going to continue on anyway. So the first part that we're going to do is just going to cover that first objective, just find values of inverse trigonometric functions. We're not going to focus really on graphing, but it is necessary to look at the graph of some of these to understand why we treat them the way that we do. So the graph that I have here is the inverse sine. Arc sine is another term for that. The graph of sine, if we had y equals sine of x, we know looks like a wave, right, going this way. That is so beautiful. So the inverse of any function is what happens when we reflect this function over the line y equals x. When we do that, if I take that function and I'm going to flip it over this line, it's going to turn it into this. And the points that make up this function, for instance, this point, this first intercept, this is at pi 0. That corresponds to the point on the graph of the inverse of 0 pi. All of your coordinates, we end up just swapping the x and y values. Another one of our key points happens here at pi over 2, 1. That's going to correspond to this point over here at 1 pi over 2. Now, one of the issues with this graph of the inverse is that if you recall what it takes to be a function, if we can draw a vertical line on our graph and it hits more than one point, in this case it would hit lots of points, that makes it not a function. So this version of arcsine is technically not a function because it fails the vertical line test. So in order to be able to call these inverse trigonometric functions, we have to limit the domain and the range so that we don't end up with multiple values hitting that vertical line. And we call those values in this restricted domain the principal values, which is one of our vocab terms. Each different trigonometric function has its own range or domain, I guess, of values that are going to make this a function and not a monstrosity like this arcsine graph. So the principal values, these are also the values that your calculator will give you back if you did like the inverse sine of something or inverse cosine of something. Your calculator is only going to give you one answer. When, for instance, if I wanted to find the inverse sine of 1, then what that means is we're looking at what angles will give us a sine of 1. Well, that happens at all of these peaks on this function, and it continues on forever. There's an infinite number of angles out there that have a sine value of 1. But your calculator is not going to give you an infinite number of answers. It's going to kick back one answer. And that answer is going to be the principal value of sine. And we denote the principal values by using capital letters for sine, cosine, or tangent. And this will get clearer as we go on and do other examples. I would suggest, while we're doing this also, that you have your unit circle in front of you, because that's going to help you determine our sine, cosine, and tangent, and inverse sine, inverse cosine, inverse tangent values. So principal values are the values of the inverse trigonometric functions and it is different. The way that we find these is going to be different, like I said, based on whether it's sine, cosine, or tangent. So we'll just make a list here. You can do this in your notes rather than in the vocab for this part. So our principal values here, they go with capital letters. So that's a capital S. Whenever you see that capital letter, if it's sine, cosine, tangent, that means that we're only looking at the principal values here. So y equals principal sine of x if and only if, meaning there are no other exceptions here, y equals sine of x, and I'm running out of room. X is between negative pi over 2 and a positive pi over 2. On your unit circle, this is going to correspond to quadrant 4 and quadrant 1. So when we're looking for principal values of our inverse sine, we are only going to be looking at angles that are in quadrant 4 and quadrant 1 that satisfy that equation. Tangent is the same as sine. So I'm going to we'll just do that one too. Y equals capital T tangent if and only if, that's not a misspelling, that's a shortening of if and only if, y equals the tangent of x, and x is between negative pi over 2 and pi over 2. For cosine, same kind of notation, capital C, if and only if y equals the cosine of x and x is between 0 and pi. So cosine principal values are going to be found in quadrant 1 and quadrant 2. Sine and tangent are 1 and 4. Cosine is 1 and 2. Cosine is the only one that's going to give us, it's always going to give us positive angles. For sine and tangent, if we do the inverse sine of something that is in fourth quadrant, we're going to get a negative angle. If we want the positive angle associated with that, so we want the coterminal angle, then you could add 360 or add 2 pi. For the purpose of your assignment on this part, it is okay to leave them as negative. So if you get like a negative 45 degrees, just leave it as negative 45 degrees. We don't need to add 360 to make that a positive 315. Your inverse functions then, we use different notation kind of interchangeably, but when we are in this section, we're going to be dealing with capital letter inverse, sine, cosine, tangent. And the other terms for those are arc sine, arc cosine, two C's, it looks weird, and arc tangent. You will either write these out. Why? Okay, hold on. I don't like this. Scooch that guy down. All of these are on page 853 as well. So arc sine, we'd shorten that to capital A, arc sine, or we do a capital S inverse. So like the exponent's like a -1. Arc cosine, same thing, arc COS, or capital C inverse cosine. Tangent, arctan, or capital T inverse -1 exponent. And when we look at the graphs of these, arc sine is going to be just this part of the graph. If you graphed this on your calculator, that should be what it looks like. Arc cosine is going to look slightly different, as will tangent. I mean, they all kind of look similar, but we have to restrict the domain because otherwise we're going to end up with a lot of values on any given vertical line. Okay, I'll just draw these in. So arc sine is this bit. Arc cosine is harder for me to draw. So 0 to pi is going to be like this, and pi over 2. It kind of looks like this. That's not a very good representation of it, but we'll work on better graphs later. Inverse tangent is like one full period of tangent. Okay, wait, this is also not very good, but these kind of go out horizontally here. In order to keep them as functions, we want to make sure that we are limiting the domain. So we're only seeing like small parts of the graph, technically. Back to our definitions here. So focusing on arc sine, I'm gonna label all of these with like what their function looks like written out. Also listing the domain and range for each of them. So arc sine, again, either one of these notations is appropriate. Equation-wise, it might look like y equals arc sine of x, or y equals inverse sine of x. The second version is what you would use on your calculator. They do not have, there's no differentiation between like a capital S or a smaller s, but the calculator is programmed to only give you back the principal values. Domain for arc sine is that your x values are between -1 and 1. Your range is going back to this inequality here with the principal values. So your y values are going to fluctuate. I don't know what word I'm thinking of. They're going to range from -π/2 to +π/2. Arc cosine, notation-wise, we'd have y equals arc cosine x or y equals inverse cosine of x. The domain for these is also -1 to 1. And here your range corresponds again to the principal values. So it's going to be from 0 to pi. Tangent or arctangent, we'd have y equals arctan x or y equals inverse tangent of x. Your domain for tangent is all real numbers. I don't know why I wrote out domain on the first and last, but not on cosine. Don't ask me why I do the things I do. I don't know. So domain is all real numbers. We can plug anything we want into the inverse tangent. That's going to continue going in both directions. But your range, again, will be the same as sine, that your y values have to be between -π/2 and a +π/2. So whenever we do the inverse sine, inverse cosine, inverse tangent, you are going to get values that are within these ranges on the calculator, and that's mostly what we're going to be doing today, is using the calculator to evaluate these things. If I do inverse sine of something, I'm always going to get back a value that is between -π/2 and π/2. Or if we're in degrees, from -90 to +90. On your unit circle, like I said above, that's going to be quadrants 1 and 4 for sine and tangent. Cosine, you're looking at quadrants 1 and 2. When we do problems with these, there's two different scenarios of what we're going to be actually evaluating. In one, you're just going to be given, find the inverse cosine of -1/2. And then we're just going to use the unit circle or the calculator to be able to evaluate that. The second scenario is going to be where you're doing a trig function on an inverse trig function. So like tangent of the inverse cosine of 1/2. In our sine, cosine, and tangent functions, the value that we are inputting to that is an angle measure. So if we're doing the sine of 90, we're doing the sine of 90 degrees, and we're getting out a value from that. When we're doing inverse sine, cosine, tangent, our output is the angle value. So again, when you have a function with, say, some point x, y, the inverse of that, we're switching the x's and y's around. Okay. If you look at your unit circle, do I have one in here? Why do I not have one in here? Hold up. Let me grab the one from here. Okay. So in our unit circle, hopefully you guys, I can't remember if we wrote the tangents all the way around. That would be really helpful. When we are finding inverse sine, inverse cosine, inverse tangent, we are looking for the angle values that give us the number that we're doing the inverse sine of. Okay, for instance, if I want to evaluate the inverse sine of 1/2, what that means is I'm looking for which angles give me a sine of 1/2. And for sine, we are looking in quadrants 1 and 4. So within these two quadrants, we're looking for which angle gives us a sine of 1/2. Well, 1/2 is right here. Our y values are our sines. So the angle that makes that happen is 30 degrees, or pi over 6. Okay. If I wrote that with a lowercase s, like this, inverse sine of 1/2 like that, that would mean give me all of the angles around the unit circle, continued indefinitely, forever and ever and ever. There's an infinite number of angles that have a sine of 1/2. It happens at 30 degrees, but it also happens at 150 degrees. I didn't mean to write that. So it's going to happen at 30 plus all coterminal angles with that, and it's also going to happen at 150 and all coterminal angles with that. An infinite number of angles as possible answers here. When we really only want one answer, it has to be our principal values in quadrants 1 or 4. So when you are doing this on the homework, these are what the problems are going to look like. Find each value, write angle measures in degrees and radians. So give an answer in both degrees and radians. So it might ask us to evaluate inverse cosine of 0. Okay, you're going to look at your unit circle and determine where in quadrants 1 or 2 is the cosine of x equal to 0. What angles or angle has a cosine of 0? If we look at our unit circle in quadrants 1 or 2, the cosine is 0. Cosine, remember, is our x values. Cosine is 0 right here. And that happens at 90 degrees. So the cosine, inverse cosine is of 0 is 90 degrees, or pi over 2. If we do the other notation, say arc sine of the negative square root of 2 over 2. Okay, this is asking us where in quadrants 1 or 4 is the sine of x equal to the negative square root of 2 over 2. Looking at your unit circle, we find where sine is equal to the negative square root of 2 over 2, which is right here in fourth quadrant. That happens at 315. But I don't want an angle that is that big. We want the negative angle that we would get going this way, so that's going to be negative 45 degrees. Whoops, that is not what I wanted to do. Okay, arc sine of negative square root of 2 over 2 is negative 45 degrees, which is the same as negative pi over 4. You can do this on the calculator I would start out by making sure that that's not the right calculator, that your calculator is in degrees. And then turn your answer into radians by using your unit circle or whatever. I think that might be easier to do. Your inverse functions are the blue ones above the regular sine, cosine, tangent. So to do inverse sine, for example, you would do second sine and then type in the value. So our first example that we did was inverse cosine of 0. So I do second cosine, 0, enter. That gives me 90. Then I can turn that into radians by looking at my unit circle or converting it. You multiply by pi over 180. What was the other one? The inverse sine of the negative square root of 2 divided by 2 gives me negative 45. I would then turn that one into radians by multiplying by pi over 180, or just using your unit circle and recognizing that that's at negative pi over 4. Inverse tangent, same exact thing. If I did inverse tangent of the square root of 3, this is going to give me an angle that's in first quadrant because it's going to be a positive. So that happens at 60 degrees or pi over 3. I would like you to first try to get the answers just by using your unit circle. Check yourself using the calculator, but it is important that you know how to do this using the unit circle, that we can look back and be able to find the correct angles, find the correct points on the unit circle, and relay that to the correct angle. But you can always fall back on using the calculator to find that answer as well. So the second part of this objective is finding like a trigonometric value of an inverse function. That sounds worse than it is. And this is going to align with example 2 in your book as well. The example that they use is to evaluate the tangent of the inverse cosine of 1/2. So the inverse cosine of 1/2, this is what angle has a cosine of 1/2. And then we're going to do the tangent of that angle. So if you look at your unit circle, you would see that the inverse cosine of 1/2 is that 60 degrees. So we're doing the tangent of 60 degrees, which I have to look at it, is going to be square root of 3 over 2 divided by 1/2. Which would actually simplify down to the square root of 3. Okay, if we did this on the calculator and they give you the same button presses there, you're not going to get the exact value. It's not going to give you back square root of 3. But we can certainly go in and type it in. And we would be doing the tangent of the inverse cosine of negative 1/2 and it gives us, oh, is it negative 1/2? No, it's positive 1/2. I typed it in wrong. JK of 1/2. Positive 1.73, which is the square root of 3. Okay, so you can always use the calculator to check, but again, I would really like you to try it, try to evaluate it with your unit circle, getting the exact values when that angle is on the unit circle, or when that point is on the unit circle. That's not always going to be the case. If I wanted the exact value for all of these, we could do that using right triangle trig. We could set up ratios and all that. For now, we're just going to focus on using the calculator to get the decimal for these ones that are not on the unit circle. For instance, the next example they have here under the guided practice 2a is sine of inverse tangent of 3/8. So 3/8 is not any of our values on the unit circle. Okay, so that means we can't use the unit circle to evaluate this one. You would have to just do it on the calculator. So we would go in and just type in sine, well, that's not it, sine of inverse tangent of 3/8, and we get about 0.35. That's not the pen. Equals 0.35. Okay, when this value is not on the unit circle, then default to using the calculator. If it is on the unit circle, however, I want you to try it without that. And not that I'm gonna, well, I mean, I guess I will know, because some of these, like for the square root of 3, if you just put 1.73, I'm going to know that you just typed it into the calculator. You did not get the exact value. For this next example, same thing. If we did the cosine of the arc cosine of negative square root of 2 over 2. So this one, just like if you're solving an equation and like adding 4 is the opposite of subtracting 4. If we add 4 to a negative 4, it cancels each other out. If I do the cosine of the arc cosine, they cancel each other out. This would just be the negative square root of 2 over 2. Because we're looking at like this, the arc cosine of negative square root of 2 over 2 is what angle has a cosine with a negative square root of 2 over 2. That happens at 135 degrees. Well, the cosine of 135 degrees is the negative square root of 2 over 2. These two functions, cosine, arc cosine, cancel each other out effectively. They are inverse functions. They undo each other. So any of these, anytime you have like sine of arc arc sine of say 1/2. We're looking at what angle has a sine of 1/2. That would be 60 degrees. So then the sine of 60 degrees is 1/2. So sine of the arc sine, again, they just cancel each other out. I'm going to assume you're maybe not going to have a ton like that. You do have at least one. And only one. Okay, so these fall back on using your calculator if this value here is not on your unit circle. If it is on the unit circle, please use that first. Double check by using the calculator. But if it's not, then you're just typing it into the calculator to get the correct values. That's pretty much it for this first objective. Tomorrow we will be doing like solving equations using this, the concept that undoing sine is doing arcsine. But for today's, it should be fairly simple. Just use your unit circle, and then double check on the calculator. The homework is going to start on page 856, and you'll do 1 through 6 and 12 through 23. If you need to check your work as you go, I've let Mrs. Hollowell know that it's okay for you to check the textbook, check my textbook. Or if you have questions, you can email me. I will try to keep an eye on that and respond back to you in real time or as close to it as I can. Otherwise, bring those questions tomorrow and we'll quickly review before moving on to the next part of this. Good luck!